Welcome to Blender add-on development for beginners. In the previous video, I explained what our goal is in this module, rigging a Bezier curve with an armature that has a bone for each control point. In this video, we are going to build the actual code, so let's get started. The beginning of the add-on should look familiar. This time we put all the imports we need at the top, and the BL info dictionary also contains no surprises. Although we have one new item, the doc URL. Once installed, this URL will be available in the add-on preferences, which is convenient for users who want to know a bit more about the add-on. The first function we create will return a list of control point coordinates. For the spline object, we pass as an argument. It implements what we discovered in the previous video and loops over all Bezier points in the spline to extract their CO attribute and convert that to a tuple. A spline doesn't have to be a Bezier spline, so Bezier points could be empty, but we leave sanity checks for the poll method function we will implement later. The next function will take care of creating the armature. It needs the context and a list of points, and also an argument to specify if we want to add an inverse kinematics constraint. We start by creating a new empty armature object and then add it to the scene. Then we switch to edit mode to add the bones and loop over each pair of points. This may look a bit complicated if you are not too familiar with Python, so let's break it down. We have a list of points. We want to create a bone from point 0 to point 1 and then from point 1 to point 2 and so forth. That is what the first two arguments of the zip function do. The first is a list starting at 0, the second is the same list starting at 1. This means that the second list will be one item shorter than the first one, but the zip function will stop at the shortest. The third argument with the range function simply counts from 0, so we can use that as an index. So all this will result in the zip function generating tuples with the first point, the second point, and an index, and this is stored in the a, b, and index variables respectively. With this information, the first thing we do is create a new edit bone with a name we derive from the index. The head of the bone, the start at this, we set to the position of the first point and the tail to the position of the second point. We also want all bones to be parented to the previous one in the chain, except for the first one. So if a parent is known from the previous iteration, we make that the parent. And then we store the current bone for the next iteration. When all bones are created, we check if we need to add an inverse kinematic constraint. And if we do, we need to change to pose mode to add the constraint. The actual constraint only needs to be added to the last bone in the chain. With all this done, we make sure we are in object mode again and return the armature object we created. The armature itself will not deform anything, so the next function will take care of adding hook modifiers to the curve. Besides the context, it needs the armature and curve objects and an extra size parameter to determine the display size of the empties we will create. We get to that in a moment, but first we make sure the curve object is the active object, and we do this by assigning it to the active attribute of the objects in the current view layer. We also assign the curve data to the data variable to save us some typing in the rest of the code. To add a hook modifier to each control point, we need to loop over each point, and then we have to make sure that this control point is the only point that is selected. We also deselect any handles, because it's possible to add hooks to handles too, but that's not what we want. The selection of individual points is done in object mode, but adding the actual hook modifier needs to be done in edit mode. So we switch, call the hook add new ob operator, and switch back again. This operator will create a new empty object and add a hook modifier to the selected control point. But we still need to make sure that the location of this new empty will be constrained to one of the bones in the armature. Now calling an operator does not return a new object, so we figure out this empty by looking at the object attribute of the last modifier we added to the curve. We then change the display type and size of the empty just to make them look nicer. The size will come from a property so the user can control this. The constraint we add to the empty is a copy location constraint, and it will be tied to the armature, of course. But we also need to tell which bone to use and whether to use the head or the tail. J is the index of the point, so if it's 0, we are dealing with the first control point. So the subtarget is the first bone, and this first point will be constrained to the head. So we set head tail to 0. All other points need to be constrained to the tail, so the second point needs to target the first bone, and the third point needs to target the second bone, etc. So that's why we subtract 1 here to get to the actual bone, and for these points we tie them to the tail, so we set head tail to 1. The hard work is over now. All we have to do is put everything together in an operator. The variable definitions at the top should be self-explanatory. And we also define the size and key properties. These will be shown to the user. Next is the poll method, which needs to make sure all the assumptions we made actually hold true. We check that we are in object mode, have an active object, and that this object is a curve. We also check that this curve has exactly one spline and that this spline is a Bezier curve. And we check if we have at least 2 control points in the spline. With the assumptions checked, we can implement the execute method, which is really short because most of the work is done in the functions we created earlier. We get the curve object and its only spline, then we calculate the list of control point locations and create the armature based on those points. We position the armature at the exact same location and orientation as the curve object by copying its matrix world attribute, and for the user's convenience, we also make sure that the armature shows up in front. Finally, we call the createHooks function to tie the curve to the armature and return finished to signal our operator is done. That is all our operator needs really, but I want to show you one final addition, a draw method. You don't need this because all properties will be shown to the user anyway, but if you want to control the layout of the panel that will be shown, the draw method, if present, allows you to do this. This implementation will replicate the default, and I will not explain it here, but I will put a link in the description to the documentation, and if you want this addressed in a future video, let me know in the comments. The last part is simply boilerplate to create a new menu entry and register our operator when the add-on is enabled. Okay, that was quite a bit of code, so let's check if it really works. We click Run Script to register the operator and then go to the Object menu. Our entry is present, and when we click it, we can see the armature and the empties. We can even change the size of the empties to our liking, and we could disable the inverse kinematic constraint. We leave that on, however, and select the armature. We switch to pose mode and select the last bone in the armature. Moving it about shows that the inverse kinematics work, but we can of course also select another bone and rotate that, for example. So all seems to work okay, so we should save our file and then install it as an add-on, but I leave that to you. So what have we achieved? Well, we created an add-on that figures out the control points inside the spline of a curve, creates an armature with a bone between each of those points, and creates hooks between the curve control points and empties that are constrained to the bones in the armature. This add-on could save a user a lot of work if they wanted to rig tentacles or cables, for example. But there is still room for improvement, of course. For example, putting the armature and the empties into a separate collection, or making this work for other types of splines. And maybe we will cover that in a future video. But for now, thank you for watching and see you in the next one.